Okay, so welcome back. So we're going to continue with constraint optimization problems. And today's goal is to consolidate what we have learned so far and basically apply them to actual word problems that might arise. So let's use our knowledge first. In the last class, we basically learned how to solve constraint optimization problems, right, using the KKT condition. Right? We In this class, we're going to essentially try to recognize these problems, these kind of problems in real life. And then to start today's process, I want you to solve this problem here, just to refresh yourself of how to use the KKT condition. So pause the video and solve this. Okay, the solution is over here. I wanted you to solve both using solve it by hand, as well as using the Python method. So this is the Python method, and over here is by hand. Okay, so now that you have a little refresher and remember the KKT condition, we can now move on. Let's use what we've learned so far and see if we can solve this word problem. Let's say it's 2030 and the world has ended due to some kind of zombie apocalypse, right? And you became the leader of a very large group of 100,000 survivors. We call ourselves the Northeastern Group. So, to protect the citizen, you decided that you should probably build some kind of protective wall because there are zombies everywhere around the new city you're building. And you want to maximize the total area. So remember, you have building a rectangle and you're trying to maximize the total area. However, your army can only realistically guard 20 miles against the zombies. So this is the constraint. What should the length and width of the rectangular city be that essentially maximizes total area? Okay, so take pause the video, take a second, and see if you can try to think through this problem and formulate an optimization problem, and then solve it. Okay. All right. So the solution is right here. Okay. You can pause the video, take a look at the solution, and the point is, in the end, you end up solving the identical problem you just solved in the very beginning of the class, where I asked you to essentially refresh your memory of KKT condition. Turns out that it was the identical problem. All right, let's see if we can solve another one. So everything about the question is the same, except this time you add an extra constraint that you want to build one of the sides between two mountains 3 miles apart. So you have two mountains 3 miles apart, and you want to make sure you build a city around that. So this is a constraint that one side of the rectangle cannot be greater than 3 miles. Okay. Now, what length and width should the rectangular city be if you add this inequality constraint? All right. Okay, pause the video. We're going to continue. You can take a second and you can study the answer right here. Okay. All right, let's solve another one. Next problem. Well, you remember from Professor Wu's classes that if you want to maximize the area while minimize the circumference, ideally you don't want to build a square. What you want is you want to build a circle like this. So ideally you have a circle. So take a quick look. If you have a circle of 20-mile circle, okay? So let's say the circumference is 20 miles because that's how much you can guard. And therefore the radius will be roughly 3.18. So the radius would be 3.18. Now, if we find the area, right, we'll be using the area of the circle equation. We will know that the area is 31.83. So compared to if we used a square, right? If we use a square of 5 by 5, this is much, much larger, right, than 25. This implies that given the exact same perimeters, perimeter length, you can get a much larger area if you simply just pick a circle. All right, anyways, so let's say that let's say that we have finished building the city, right? And we need to decide where to put the door. And the door has a lot to do with our trading partners. So our trading partner, our largest trading partner is MIT. Unfortunately, BU was destroyed, so BU is not there anymore. And so the point is, the trading post is right by the Charles River Bridge, right? So right here, the Harbor Bridge. So ideally, because traveling is dangerous, there's zombies everywhere. So you want this distance to be as small as possible. Okay. So in this question, your goal is to try to identify the location. You want to identify the location of this door along the where you want to put the door along your circular city such that this distance is minimized. Okay. Now we're going to assume the center of the city is 0, 0, and then the bridge is at the point of 4, 6. So this is the 4, 6. Okay, so that's where the bridge is, and you want to identify the location of the door such that the distance to the trading post is minimized. Okay, take your time, think through this, and you also want to solve this with by hand as well as with Python. Okay, all right. So over here is the solution. Basically, you're trying to find the distance, and you use the distance equation, and you're trying to minimize that given some kind of constraints. Okay. And over here is the Python code. You can see that the best location will be right here. If you draw essentially like a straight line, so this would be the best location. All right. Next question. Where should we put the army? Well, now that we've constructed this circular city and we have the northern gate and the southern gate, which we use the southern gate to trade with the Roxbury neighborhood. So, so the currently the city essentially has two weakest points where zombie might attack, which is here and here, and the locations are this one for this one for this. So you know the location. So you need to decide where to put your military. Right? Basically, you want the travel distance to be as small as possible. Wherever your military is, you want the distance to be as small as possible. However, the military is currently also being used as a police, uh, so it can't be more than 1 mile from the city center. So here's the city center. You want this to be as small as possible, but it cannot be more than 1 mile because you need to come to the downtown to basically, I don't know, enforce laws or something. So, anyways, now let's try to solve this problem. Okay, first without Python, then use Python. Okay. All right. So over here is the solution. You can pause the video, study the solution, and that's it for all the major word problems. Okay, so the next part we're doing is this concept called duality. So we previously learned KKT condition, right? We can use the 4 KKT condition to help us solve the constraint optimization problem. And now let's return to our initial optimization problem. This one we've been solving all day today. So this is the same problem we have been solving. And if we simply convert this into a Lagrangian, it will look something like this. Right? So here's the original function, and here's the equality constraint. Now, instead of trying to solve both x1, x2, and lambda, instead of trying to solve everything at once, sometimes what we can do is convert this problem, this Lagrangian, into an alternative, equivalent, but simpler formulation. So we can convert this into a different type of problem that's simpler to solve. And this other type of problem is called the dual formulation. So when we find a Lagrangian, this is called a primal formulation. So we start with a primal. And sometimes if we convert, if this is hard to solve, we convert this formulation into a dual formulation, then it becomes easier. So we're going to go over the general idea of how to do this. So the let's say what is the dual formulation, which denoted by the function you're trying to optimize, d. Well, d, this function, is simply the original Lagrangian, assuming that you do know the optimal x already. So you found only the x. So what you do is once you found the x, right, in terms of lambda and gamma, you plug the x back into this equation. So you only have the problem in terms of lambda and gamma. So let me show you what it means. Okay, so this is the dual formulation. So we're kind of solving it in stages. Instead of solving x1, x2, and lambda, we'll just look at x1, x2 first, right? So what is the derivative? So let's use the stationarity condition. So we basically want to take the derivative with and set the derivative with respect to zero. Okay, so we take a look at this. Right? If we take the derivative with respect to x1 and x2 and set the result to 0, then it will tell us that x1 is equal to minus 2 lambda, and x2 is also equal to minus 2 lambda. So this means that we now have x1 and x2 in terms of lambda. And so we can essentially plug x1, x2 in terms of lambda into the original equation. So the problem is only with lambda now. So if we plug x1 and x2 in here, x1, x2, sorry, x1, x2, and then for every x1, x2, I just plug x1, x2 in here. So now all we're solving is a lambda problem. Nothing else. This is it. The dual problem, once you have kind of identified the dual problem, is when you are trying to maximize the dual problem given the same constraint. Now, this constraint and this constraint looks different, and that's only because I plugged in x1 and x2, right? If I plug in x1, x2, it will give us plus 8 lambda. So the dual problem basically comes when you first solve for x and then plug the x into the original problem. Once you plug it into the original problem, you got a new problem. And this problem is a lot simpler because instead of trying to solve x1, x2, you only have to solve lambda. Right? So you can see that we removed a lot of variables. Now this example, we only have x1, x2. But you can imagine if we have x1, x2, x3, x100, right? A million of them, and then we reduce like 1,000 variables down to just one variable. So that drastically simplifies the problem, and this is why dual formulation was invented. Okay, so okay. Now the obvious question that most people will ask is, I thought we were minimizing. Why are we maximizing the dual problem? Well, that's got to do with geometry. When you have the primal problem, you're trying to find the minimum, right? So this is the primal problem. It turns out that once you've already discovered the minimum x, the dual problem looks like this. And you're trying to find the maximum. Okay? Now, that is very interesting, and there's the proof for this. I will quickly go over the proof. I mean, as long as you remember the primal and the dual opposite, maximization and minimization, that's good enough. But if you're curious, the reason is because the dual is defined as the minimum solution given x, right? So that's dual. And we know what Lagrangian is defined as. The Lagrangian is the function, equality constraint, and the inequality constraint. So now we have all three. And when you find the optimal x, this implies that the equality and the inequality constraint must be met, implying that the equality has to equal to zero, and the inequality has to equal to zero or less than zero. So that's literally the point of the inequality. Remember, we always set up the inequality to be less than equal to zero, right? So okay, so if we found the optimum x, right, then we remember this is the dual formulation, which is defined this way. And then if we plug in the optimum x, then this is the Lagrangian. So this is the Lagrangian. The Lagrangian has the function. And notice that if we have the optimum solution here, this has to be zero. And this has to be negative or zero, right? So you have the function plus some kind of negative value, implying that whatever you have here has to be less than the function, original function itself. Kind of look like this. So this right here is the original function. And it doesn't matter what the solution is. The, the solution for the dual is always less than or equal to the function itself, right? So the solution has to be less than or equal to. And that's why you're trying to find the maximum. Now, this right here is a quick summary. You would need to, if you really want to understand why this work, you want to kind of like study this a bit and think through the logic. Okay. For the purpose of this class, I'm not going to test you on this. So, don't worry about it. All right. So the best way for you to learn is basically do it yourself. So for this problem here, right, solve the problem first using the primal, using the KKT condition, and now convert the problem into a dual and try to solve it. And then you can double check the primal solution is the same as the dual. They're supposed to be the same, by the way. Okay, so pause the video. This is the next exercise. I provided the solution here. You can also take a look. And over here is yet another problem, right? Does this doing learning this just requires you to kind of get your hands wet and do it multiple times. So try again, pause the video, see if you can do this. Okay, and the solution is right here. All right, now if we put everything together, the Boston colony. So we also trade with the Boston colony, which is right here, right? And what they do is they jump on a green line based on this line here, and then they try to trade with us. Okay, so that's the Boston colony, and they trade with us by jumping on the green line. And for simplicity, the equation for the green line is this, where the center point of the city is 0, 0. So this is I gave you the equation for the green line. So due to our trading relationship with MIT, we already figured out where the door is supposed to be, right? So this is where the door is, which is I think was this when we found out. Okay, so when they're going on the green line, they're also trying to minimize their distance to our door. So where along the green line would the Boston colony have to jump off the train to minimize the distance to come to our door? Okay. So now try to formulate this, solve it with the KKT with the dual formulation, and then you can use NumPy to double check. Okay. Now remember the trading point was with MIT is 4.6. Um, and then okay, so the first part is where would they have to jump off to trade with us? How about this? The second part is where would they have to jump off to minimize the distance so they can trade with MIT at this location? So those are the two questions. And I think that's it for today. Yeah, this is it for today. Yep. Good luck with solving this. This just takes a lot of practice. Have a good one.